Hello, I am beyond overjoyed to introduce you to our fifth chapter in our exploration of the world of calculus. And in this chapter, we will be studying transcendental functions. So this chapter will be broken up into a series of videos, and each video will be exploring a separate topic or certain types of functions. So today's video will be focusing on logarithmic functions and exponentials, and perhaps we'll have another video on trigonometric functions and inverse trigonometric functions, stuff like that. So be on the lookout for those videos. But as I mentioned, today's video will be about exponentials, logarithms, and all of the sorts. So be ready to see a lot of ln's and e to the x's thrown around. We're going to be feeling very comfortable with differentiating and integrating those functions by the end of this video. Let's jump into it. So we'll start by talking about the natural log. So there are many different types of log. The logarithmic function can have many different bases. We see log base 2, log base 10, those are like the most common. In calculus, we use the natural log the most because it has base e, and we commonly work with e to the x functions. So the natural log is where we'll spend most of our time, but we'll also learn how to deal with different base logs. So just a brief review about what the natural log is. We'll recall some basic facts and properties about the natural log. Remember that it's defined for all positive real numbers. So like ln of 0 does not exist. ln of like negative 8 also does not exist. So any negative value we can't plug into the natural log, and same thing with 0. So we have ln of 1 equal to 0, and the way we can think about this is e to the power of 0 equals 1. So let me just use some colors. So e to the 0 equals 1, and this is the 1 right here, and that's the 0. So that's how we read the natural log. Also, if we are taking the natural log of the product of two values, we can split that into the sum of the natural log of the individual factors. So this is a really important property and one that we should be feeling comfortable with. Another equally useful property is when we're taking the natural log of some exponent, some power, and we can bring down this n in front of the natural log. So this is equivalent to n times ln of a. And this property can actually be seen from the property right above it. We can think of a to the n as a times a times a n times, and that would just equal ln of a plus ln of a plus ln of a n times, so we get n times ln of a. And then our last property kind of links with our second property, but now we're taking the quotient of two elements, so a divided by b, that would be ln of a minus ln of b. So these are all things that we should know and be feeling comfortable with. So now the natural question, pun may be intended, is what's the derivative of the natural log? So we'll let u be a function of x here. It's a function. Then the derivative of the natural log of u is equal to 1 over u times the derivative of u. So we do 1 over whatever this value is, and then we multiply by the derivative of this u with respect to x. And then these two properties are very similar to each other. The only difference is we throw in some absolute values here. And we'll see later why we like to see the absolute value bars, but we should note that the derivative of the natural log of the absolute value of u is also equal to 1 over u du. So now we'll take a look at the integral. So if we take the integral of 1 over x, that's going to be equal to the natural log of the absolute value of x plus c. So this is by our definitions. We see here the absolute values are thrown in, so that's why we had this property up here to relate the two, right? So we're taking the antiderivative of this, and we should get that, and that's exactly what this property is saying here. So integral of 1 over x that you associate with natural log. Okay, so let's try to work with what we know now. And our first question asks us to find the derivative of y equals ln of the absolute value of sine of x. So we know that the derivative of ln of the absolute value of u, that's going to be equal to 1 over u times du. And remember, u is a function of x. So in this case, what would u be? Well, if we let u equal sine of x, then we have ln of sine of x, absolute value, equals ln of the absolute value of u. So that means if we were to take the derivative, which is what we're trying to find, we can take the derivative on both sides, and that we know is equal to 1 over u times du. So now it simply requires us to plug back in what u is and take care of it. So that would equal 1 over sine of x, because that's what u is. And then du would be the derivative of u with respect to x. So the derivative of sine of x is equal to cosine of x. So we can simplify this, cosine x over sine of x. And if we're feeling fancy, we can call this cotangent of x. And that's our answer. So yeah, that's our first application there. So the main trick is when we see ln, we do 1 over the function and then multiply it by the derivative of that function. That's the habit we'll want to get into. Let's do another one. Again, finding the derivative, but now we're trying to find the derivative of ln of y equals x squared times ln of x. So this seems like it's going to require some implicit differentiation, since we have ln of y on this side. So let's try taking the derivative of both sides with respect to x. So d dx of ln of y is equal to d dx of x squared times ln of x. So on the right-hand side, it looks like we might have to use the product rule. But let's do the left-hand side first. So remember, with implicit differentiation, we differentiate the function of y as normal, but then we throw in that dy dx when applicable. So the derivative of ln of y, that would be 1 over y, but then we have to multiply by the derivative of y. Remember, if we go back here, the derivative of ln of u is 1 over u times the derivative of u, where u was a function. So in this case, we can link y being a function of x, so the derivative of y with respect to x is simply dy dx. And on the right-hand side, let's use the product rule. So that would be the first times the derivative of the second, plus the second times the derivative of the first. So let's simplify that. On the right, we get x squared times, well, the derivative of ln of x. We know this now, that's 1 over x. So we'll put that in. Plus ln of x times derivative of x squared, the good old power rule that we learned a while ago, that's 2x. And on the left, we'll keep 1 over y times dy dx. Okay, so let's simplify things a little bit. Keep the 1 over y times dy dx. And then here we get x squared times 1 over x is x, plus 2x ln of x. And remember, we're solving for dy dx, so we should multiply by y on both sides. And we'll get dy dx equals x plus 2x ln of x times y. And what we could do here is sometimes we don't like to see this y in the right-hand side when we're solving for dy dx. So we can substitute for this y. And for that, we'll have to look up here. If ln of y equals x squared times ln of x, then that means that e to the ln of y equals e to the x squared ln of x. And e to the ln of y, when we were talking about our logarithmic properties, we showed that that's equal to y. So y equals e to the x squared ln of x. So if we want, we could plug this back in here and get x plus 2x ln of x times e to the x squared ln of x. For some of the future problems, I won't always do the substitution, but this is just something that you should be aware of and something you can do, because now our dy dx is expressed only in terms of x. Sometimes it's not as easy to do that substitution, but this is something you should be aware of. Cool. Let's do this one. Find dy dx for y equals that. And perhaps you're pausing for a moment and you're like, I don't see a natural log. I don't see an e to the x, even though we don't really know how to take the derivative of e to the x just yet. What's going on here? And maybe you're thinking, let's use the quotient rule. And we very well could use the quotient rule. But what you'll quickly realize is that the quotient rule will be very, very annoying and disgusting to use. Which is fine. It's perfectly okay to do that. But I'm going to show you a little trick, which speeds things up just a tiny bit. So what we could do is, it's a little bit nasty on both sides. So let's see what happens when we take the natural log of both sides. So ln of y equals ln of this massive quantity over here. And the reason why we're taking the natural log on both sides is so that way on the right-hand side, we can take advantage of the natural log properties. Because now we have this quotient which we can break apart into the difference of two natural logs, right? So ln of y is now equal to ln of x times x squared plus 1 squared minus ln of the square root of 2x cubed minus 1. And okay, it's still a little bit messy, but it's not as bad, perhaps. And we can even break it up further. This x times x squared plus 1 squared, we can break that into the sum of two natural logs. So let's do that. ln of x plus ln of x squared plus 1, quantity squared, minus ln, and instead of square root, I'll use the 1/2 power. And it's a little bit better, but we're going to make it even more better because of the natural log properties. Remember, when we have powers, we can bring them out in front. So let's do that. I'm just going to erase what I did here, and bring that 2 out front here. And similarly here, we have a 1/2 power. Let's just bring that out in front. So we'll erase that. And bring out a 1/2. And on the left, we still have ln of y. And this looks a little bit easier to handle, right? We're going to have to do some implicit differentiation because we have that ln of y on the left-hand side. But I don't think implicit differentiation is as scary as doing the quotient rule for this, where I can assure you I will make some sort of arithmetic error. So let's do implicit differentiation. So we're going to take d dx on both sides, d dx, and for this right-hand side, we know that the derivative can distribute amongst adding and subtracting. So it'll be d dx of the first term plus d dx of the second term minus d dx of the third term. So we'll do the left-hand side first. This is basically the same thing we did in the last question, but we'll speak through it again. So we take the derivative of ln of y as normally, so that would be 1 over y, but then we have to multiply by the derivative of y with respect to x, so that would be dy dx. And on the right, the first term, d dx of ln of x, that's just simply 1 over x, plus, well, the derivative of 2 ln x squared plus 1. Let's just zoom in here for a moment. What we're going to do is we'll bring out this 2, because we know that we can do that with derivatives. And so this 2 will carry down, and then ln of x squared plus 1. So the general pattern is we do 1 over that quantity, x squared plus 1, and then take the derivative of that quantity. So this would be 1 over x squared plus 1 times d dx of x squared plus 1. And then for the third term, it's the same thing. So we'll bring out the 1/2, do 1 over the quantity, 2x cubed minus 1, and then multiply that by the derivative of that quantity, 2x cubed minus 1. And now we simplify and pray that we don't make any mistakes. 1 over y dy dx stays the same. 1 over x stays the same. So this would be 2 over x squared plus 1. The derivative of x squared plus 1 with respect to x is simply 2x, so we'll multiply the numerator by that. On the bottom, or on the third term, we have 1/2 times 1 over 2x cubed minus 1. Derivative of 2x cubed minus 1, that's going to be 6x squared. And let's simplify a little bit more. So 1 over y times dy dx equals 1 over x plus, here we have 4x over x squared plus 1. And then we have this 2 canceling with this 6 to make 3x squared. And on the denominator, we have 2x cubed minus 1. And we're solving for dy dx, so we just got to multiply by y on both sides, and we'll get dy dx equals 1 over x plus 4x over x squared plus 1 minus 3x squared over 2x cubed minus 1 times y, but y is given for us right here. So we will substitute this quantity in where we see y, so we'll get rid of that, and replace it with x times x squared plus 1 squared over square root of 2x cubed minus 1. So this is our final answer. It's a huge, huge expression, and it still required a ton of steps, but imagine doing this with the quotient rule, and oh my gosh, it would be quite the nightmare because it would require a nested product rule, chain rule. So this is a trick you can use when sometimes the quotient rule doesn't look pleasant. Just take the natural log on both sides, use your log properties, and implicitly differentiate. Cool. So now let's move on to some integration. Evaluate the following integral: 1 over 4x plus 1 dx. Well, we know that the integral of 1 over u du is going to be ln of u plus c. So we just we'll try to get it in this form because we don't really know how to integrate this any other way. So what if we just let this 4x plus 1 equal u? So u equal 4x plus 1. Du equals 4 times dx, so that means dx equals du over 4. So our integral becomes 1 over u times dx is equal to du over 4. So that simplifies to 1/4 times 1 over u du, and we can bring out that 1/4. And well, we know how to take the integral of 1 over u now. That's equal to the natural log of the absolute value of u. So this would equal 1/4 ln of u plus c. And the last thing we have to do is substitute u equals 4x plus 1. 1/4 ln of 4x plus 1 plus c. And that's our answer. And to check this, we can do a test of taking the derivative of it and seeing if we get the integrand. So let's try to take the derivative of this in our head. So it would be 1 over the quantity 4x plus 1, and we multiply that by the derivative of the inside, which would be 4. So 4 times 1 over 4x plus 1. But that 4 cancels with this 1/4, so we're just left with 1 over 4x plus 1, and that is what we had as the integrand. So it's always good to do that double check. So that was our warm-up integral. Let's move on to this one. It's a little bit more challenging. And, well, maybe we won't need natural log for this at all, but we can think about how to approach this, and yeah, so maybe you're running through some options, thinking about doing some u substitution, or expanding out that polynomial. Both would be a good first step. Let's try doing u substitution. So I'm going to choose this x plus 1 in the denominator because I like choosing things in the denominator because it's easy to cancel things out with the numerator. So let's choose u equals x plus 1. That means du equals dx. So that means our integral is 2x over u squared times du. Well, that's not good, because we didn't cancel out the x. So what happens if we use u equals x plus 1 quantity squared? Well, if we take the derivative of that, that would be 2 times x plus 1, and we still can't cancel with this 2x. So hopefully you remember when we were learning u substitution that there's some sneaky tricks we can do. So even though we didn't cancel out this x, we have x in terms of u here, right? This tells us that x is equal to u minus 1. So let's substitute that in. 2 times u minus 1 all over u squared du. Now we're in business. Our integral is in terms of u. It's not very simple right now, but it's in u's, which is what's good, what's important. So let's work with that numerator a little bit. That tells us 2u minus 2 all over u squared du. And then we can break apart that fraction into 2, right? We can say that's equal to 2u over u squared minus 2 over u squared du. And then the integral can split, so we have like 2 separate integrals, and we can solve them separately. So the first one, the 2 we can bring out front, and then, so that gets rid of this 2. And then 1u cancels with this, so we're left with 1 over u du. And for the second integral, we'll factor out a 2, and we're left with 1 over u squared du. So for the first one, we know how to solve that. That's 2 times the natural log of the absolute value of u. For the second one, 1 over x squared. It's almost what we know. We know 1 over x, but 1 over u squared. We know 1 over u. This is something that always tripped me up when I was learning about ln's and natural logs, is that 1 over u squared, it seems like it uses the natural log. But what happens if I rewrite it as u to the negative 2 power? Now it's just a power rule question. The reason why we can't use the negative power when we're doing 1 over x is, just draw this box here. If we wrote 1 over x as the integral of x to the negative 1, then when we do our thing of raising the power by 1 and dividing by that new power, we don't know what x divided by 0 is. We're not allowed to divide by 0. So that's why we can't do that here. But since we have u to the negative 2 power, we can do that. So, in this case, we have to do u, raise the power by 1, so that becomes negative 1, and divide by the new power. So that would be dividing by negative 1, so let's just get rid of that and change the minus sign to a plus sign. And then, of course, add c. And now we just have to substitute where we see a u. So, whoops, that's equal to 2 ln absolute value x plus 1 plus 2, I'll do a fraction for this, x plus 1 plus c. And that's our answer. So yeah, as we're building up our skills with integration and derivatives, don't forget about some of these tricks and these sneaky little things we can do. Especially making the substitution here, sometimes those are so hard to see, but it's always good to have that in the back of your brain whenever you're stuck on an integral. Just think, can I make this kind of substitution? And then don't forget, when we have a fraction, we can split it apart, especially when the numerator is being added and subtracted. When the denominator has multiple terms, it's not as easy, but we'll learn about that in the future, perhaps. So excellent. Let's try another integral. X squared minus 4 over x. So I was just saying we can split apart the fraction when we see multiple terms in the numerator. So let's do that. That will be the integral of x squared over x minus 4 over x dx. And that's the integral of x squared over x dx minus the integral of 4 over x dx. Do a little bit of simplification. X dx minus 4 integral 1 over x dx. And both of these integrals we can handle at this point. Integral of x is 1/2 x squared. Integral of 1 over x is ln of the absolute value of x. Throw in that plus c, and we are golden. So that one was a little bit easier, but again, using that trick of splitting apart the fraction. A very, very helpful trick. Let's do another one here. Ln of x squared over x. Seems tricky, and maybe we could split apart the fraction, but now there's things being multiplied, so it's like, maybe not. So probably we'll have to resort to u substitution. Now the question is, what u do we choose? If we choose u equals x, then when we have du equals dx, we're not going to be able to cancel anything with anything. So that means we have to probably choose a u that deals with this ln of x, which seems nasty, but we're going to do it anyways. So let's let u equal ln of x, because why not? Du equals 1 over x times dx, so that means dx equals x times du. So let's do the substitution. The numerator gives us u squared, and that's still divided by x. And that dx will replace with x times du. And we see that, hey, we can cancel x's. So it's weird, using ln of x as our u, but look at how nicely it cancels. So we cancel this x with x, and we're left with the integral of u squared du. Simple power rule, 1/3 u cubed plus c. And now substitute in your u, which was ln of x. So 1/3 ln of x cubed plus c. Excellent. So sometimes it's not fun choosing a nasty u like ln of x, but sometimes it pays out. So always be on the lookout for that. So that concludes the first section of this video where we're talking about natural logs. Now we're going to talk about e to the x and different types of exponentials. The great thing about e to the x is that it doesn't change too much. And there are some similarities with the natural log, at least with the derivatives and integrals. But e to the x is kind of our friendly function, and we'll see why. But first, some properties about e to the x. We have a nice little graph here of what y equals e to the x looks like. And these are some helpful things to remember. The natural log of e to the x is equal to x, and e to the ln of x equals x. So the ln and the e sort of cancel each other out. They're inverse functions, which is something we'll be talking about, I believe, in the next video. So the domain of the function is negative infinity to infinity. The range is 0 to infinity, so it's never negative. It's continuous and increasing on the domain, so it's never decreasing. So you can start to think about what the first derivative of the function tells us. And then it's concave up on the entire domain, so that gives us some indication about the second derivative. Take a look at some more properties. These are somewhat reminiscent of the natural log. So e to the a times e to the b, we just sum the powers. We're taking the quotient of 2, we take the difference of the powers. So that's similar to our normal power rules when we have a different base instead of e, same thing. The limit as x approaches negative infinity of e to the x is 0. So we can think about that here, that there's sort of like an asymptote right there. In fact, it is an asymptote. And the limit as x approaches positive infinity of e to the x equals infinity. And we can see that it's continuing going up, it's concave up, it's constantly increasing. So yeah, it makes sense that this would go towards infinity. So just some things to be aware of. Let's talk about the derivative of e to the x. So again, we'll let u be a differentiable function of x. Then the derivative of e to the u is equal to e to the u times du. So it didn't change. This e to the u stayed the same. But here's an example, right? In this case, u equals 2x minus 1, right? It's a function of x. So the derivative of this, what we do is we maintain what we're keeping the derivative of. That is part of our answer. And then with that, we multiply the derivative of that exponent. So the derivative of 2x minus 1 is 2. So we multiply our answer by 2, and we get 2e to the 2x minus 1. So that's kind of the two-step process. Keep whatever you're trying to differentiate. Don't change it. Keep that in your answer. It'll feel weird at first, but it is the correct thing to do. So keep it, and then multiply by the derivative of your power. Let's do an example. d dx of x squared e to the 4x. Seems like we'll need the product rule here, and in fact we will, because we don't know how else to take the derivative of it. So the product rule says first we do the first function, multiply that by the derivative of the second function, and then add the second function times the derivative of the first function. And all that is what we're trying to find. So x squared carries, and then d dx of e to the 4x. So taking the derivative of e to the 4x. Follow the two-step plan. Keep what we're trying to find the derivative of. And to that, multiply the derivative of the exponent. So the derivative of 4x is just 4. That's all you have to do. To that, we'll add e to the 4x. Derivative of x squared is 2x. And then we can just condense things a little bit better and get this as our final answer. So this is why I called e to the x a friendly function. It doesn't change all that much. You just keep it as is and multiply by the derivative of the exponent. Get that in your brain and you will be golden. Let's try this. Determine dy dx for y squared equals 2e to the xy. So this seems like it's going to require some implicit differentiation. So let's do it. d dx of y squared equals d dx of 2e to the xy. We're just taking the derivative on both sides. So for the left-hand side, we take the derivative of y as normal, so that would be like 2y. And then we multiply that by the derivative of this y. So that would be dy dx. And on the right-hand side, well, let's see, that's going to be 2 times the derivative of e to the xy. So how exactly are we going to handle that? Well, same way as normal. Keep the value and then multiply by the derivative of the exponent. So this will be 2 times e to the xy times d dx of xy. And on the left we have the same thing. So now to find this, we might have to use the product rule. So let's try doing that. Let me just rewrite what we have. Equals 2 times e to the xy times, okay, so product rule would say x times d dx of y, first times derivative of the second, plus second times derivative of the first. So that gives us 2y times dy dx equals 2e to the xy times, did I forget a plus sign somewhere? No, I think I'm good. Times x times d dx of y is simply dy dx, plus y times 1. Derivative of x is 1. And we're trying to solve for dy dx, so we're trying to solve for this factor. So what we'll do is we'll distribute this 2e to the xy, then bring this entire term to the left-hand side, and then factor this out. That's the game plan. So let's do it. 2y times dy dx equals 2x e to the xy times dy dx plus 2y e to the xy. So now we'll subtract both sides by that second term. 2y times dy dx, sorry about the handwriting, it's tiring. And all of that equals 2y e to the xy. So now we'll factor out this dy dx term and then solve for it. So dy dx times 2y minus 2x e to the xy equals 2y e to the xy, and now we can just divide by that term, and finally we get dy dx equals 2y e to the xy all over 2y minus 2x e to the xy. And that is our answer, I hope. Yes, it is our answer. So quite a bit of work there. Lots of product rules in there, and implicit differentiation. But all of this is to just get our feet wet and be comfortable with e to the power of different things. Remember, when we see e to the power, we should be feeling really comfortable. Keep it the same, multiply by the derivative of the exponent. Let's keep it rolling. We want to find the first derivative and second derivative of f of x equals that. So for the first derivative, it seems like we'll need the product rule once again. So that would be 3 plus 2x times d dx of e to the negative 3x plus e to the negative 3x times d dx of 3 plus 2x. So this 3 plus 2x stays. D dx of e to the negative 3x, well, we know we have to keep this e to the negative 3x. Then we multiply by the derivative of the power. So the derivative of negative 3x is negative 3. So we toss in a negative 3. And now we have e to the negative 3x times derivative of 3 plus 2x is just 2. So now we can combine this all together. Negative 3 e to the negative 3x times 3 plus 2x plus 2e to the negative 3x. And that would be our first derivative. We can actually make this a little bit simpler, and we should, because we're trying to find the second derivative as well. So dealing with that isn't very fun. So sometimes it's nice to distribute this and see what we get. So that would be negative 9e to the negative 3x minus 6x e to the negative 3x plus 2e to the negative 3x. And we see that this negative 9 and positive 2 terms are like terms. So that would equal negative 7e to the negative 3x minus 6x e to the negative 3x. And that's our first derivative. Now we need to find the second derivative of x. So that would be equal to, we're just going to take the derivative of this So we'll bring out the constant term and take the derivative of e to the negative 3x, and then we'll do minus 6 times d dx of x e to the negative 3x. So this first term here, we can handle that. In fact, we just solved for that up here. So this would equal negative 7 times e to the negative 3x times negative 3. And then here we have minus 6 times, seems like we'll need the product rule again. Oh, I'm getting tired of it too, don't worry. So that would be x times d dx of e to the negative 3x plus e to the negative 3x times d dx of x. Do a little simplification on this first term. That gives us 21e to the negative 3x. And then we're subtracting 6 times x times d dx of e to the negative 3x. You better have this memorized now. It's the third time we're doing it. E to the negative 3x times negative 3 plus e to the negative 3x. d dx of x is just 1, so we don't need to add anything. And let's try simplifying it a little bit, trying to get a nice answer. 6 times negative 3x e to the negative 3x plus e to the negative 3x. So that's equal to 21 e to the negative 3x plus 18x e to the negative 3x minus 6 e to the negative 3x. We see that this term and this term are like terms. So we get 15e to the negative 3x plus 18x e to the negative 3x. And that is our answer. So more practice with e to the x. Hopefully now you know the derivative of e to the negative 3x. I know I won't forget it, but that is our answer. Just more practice with derivatives. So now what's the integral of e to the x? Very common question. And it should follow that the integral of e to the u du equals e to the u plus c, because it's just the antiderivative. And if the derivative basically stayed the same, then we expect the integral to. So that's why e to the u is friendly. So we're going to try to get our integrals into this form, e to the u, and then we'll be able to take the integral of it. So here, we have the integral of e to the 3x plus 1, which is almost what we want. We want it in terms of u, so why don't we just let u equal 3x plus 1. du should equal 3 times dx. So now our integral reads e to the power of u times dx is equal to du over 3. So this equals 1/3 the integral e to the u du. We just saw up here, that's equal to e to the u plus c. So this is 1/3 e to the u plus c. You got to substitute this u back in, so it's in terms of x. 1/3 e to the 3x plus 1 plus c. Let's do a quick sanity check. Try to take the derivative of this in our heads. So the derivative of e to the 3x plus 1, we keep this term, multiply it by the derivative of this power. So the derivative of 3x plus 1 is 3. That 3 will cancel with this 1/3. So we're just left with e to the 3x plus 1, which is exactly what we found here. So we did get the right answer. Cool. Let's do this one. This one seems a little bit tougher. And you know, we're doing a quotient and it's a definite integral. I don't know about you, but I'm feeling u substitution. So let's do that. And again, it comes down to choosing a good u. I like to deal with the denominator because it's easier to cancel with the numerator that way. So let's let u equal 1 plus e to the x. du equals, well, derivative of 1 is 0. Derivative of e to the x is e to the x times the derivative of the power, and the derivative of x is just 1. So the derivative of e to the x is just e to the x. And don't forget your dx. So that means dx equals du over e to the x. we'll rewrite our integral. So integral will take care of the limits in just a moment. E to the x divided by u, and we multiply with that du over e to the x. And we'll see that things are going to start to cancel, but let's take care of our limits. Here x equals 0, so when x equals 0, u equals 1 plus e to the 0, which is 1 plus 1, which is equal to 2. And then when x equals 1, u equals 1 plus e to the 1, which is just 1 plus e. So let's change our limits. The bottom limit is 2, and the top limit is 1 plus e. And we can see that this e to the x and that e to the x cancels. So we're left with the integral 2 to 1 plus e of 1 over u du, and that we know how to integrate. That would just be the natural log. So this would be ln of the absolute value of u evaluated from 1 plus e down to 2. So that's equal to ln of 1 plus e minus ln of 2. And if we're feeling fancy, we can do our natural logarithm tricks and say that this is the natural log of the absolute value of 1 plus e over 2. That's our answer. So just tossing in some u substitution with e to the x and ln, now we should be feeling a lot more comfortable with these functions, which is the goal of this video. Let's do another one. This one kind of looks similar to the previous one, so perhaps we'll have to do some u substitution, but maybe not. In the previous one, this addition thing was in the denominator. Now it's on the numerator. So why don't we try using that trick from earlier on in the video of splitting up the fraction into 2. So this is equivalent to 2 over e to the 3x plus e to the x over e to the 3x dx. And we can split this apart even further into 2 times the integral 1 over e to the 3x dx plus integral e to the x over e to the 3x dx. So it's arguably better, maybe not, but okay, let's see. The first one, I don't like that fraction type thing, so we're just going to make it a negative power, e to the negative 3x dx. And then here we have e to the x divided by e to the 3x. So this is where we use that difference of powers type thing. So we take the difference of those two values and we can rewrite this as e to the negative 2x dx. Okay, that's feeling a little bit better, because this e to the negative 3x thing, we can deal with that. That feels kind of similar to what we did up here. It'll require a u substitution, but that's not too bad. So let's handle the first one, first integral, and then we'll do the second. So we'll let u equal negative 3x, du equals negative 3 dx. So now we have 2 integral e to the u times du over negative 3, and we're still tagging along this integral. So that's going to equal negative 2/3 integral e to the u du plus that other integral dx. And now we can handle this integral of e to the u. We know that's just e to the u. So we're left with negative 2/3 e to the u plus this other integral e to the negative 2x dx. Let's substitute this u back in where we see that u. It's equal to negative 2/3 e to the negative 3x plus integral e to the negative 2x dx. So now for the second integral, we'll need u substitution again. So we'll call this, we can call it u, but just to cosmetically differentiate from the previous u, let's use u star. And that's equal to negative 2x. So du star equals negative 2 dx. So now we have negative 2/3 e to the negative 3x plus the integral of e to the u star times du star over negative 2. And then just keep on plugging away at it. Negative 2/3 e to the negative 3x. We'll factor out that 1/2 term. We're left with e to the u star, du star. And that's just going to be e to the u star. So negative 2/3 e to the negative 3x minus 1/2 e to the u star. But now we have to substitute this u star back in. And we're going to get our final answer, negative 2/3 e to the negative 3x minus 1/2 e to the negative 2x. Don't forget your plus c. There we go. So that's dealing a lot with these types of integrals, integrals of e to the some power. So when we see that, use your u substitution, get it into this form, e to the u, and then take it from there. Excellent. Let's do this one. This one looks nasty, but I promise you it's not. This one requires a little bit of finesse, but not too much. It's just a scary first step. So again, we could try splitting up the fraction into two, where we have this as our first term, and then this is our second term. But there's not really much purpose in doing that because our denominator is still really nasty. And I don't really know any other way of solving this besides u substitution. So, at least with what we have thus far, u substitution is probably the way to go. So now we have to choose a u. Like I said, like to start with the denominator because that's what works best in most cases. So let's let u equal e to the x minus e to the negative x. Du, what's that going to equal? Well, derivative of e to the x is e to the x minus, now we want to take the derivative of e to the negative x. So we keep that e to the negative x, multiply by the derivative of the power, which in this case is minus 1. So let's just get rid of that minus 1 and change this to a plus sign and say that is what we have. So let's rewrite our integral. This becomes the integral of e to the x plus e to the negative x over u times du over e to the x plus e to the negative x. And we see we're going to have a cancellation here. Cancel, cancel. Integral 1 over u du. ln of the absolute value of u plus c. Do our substitution, e to the x minus e to the negative x plus c. So this one, not too tricky, just that scary first step. But again, a little bit more practice. This is really helpful to know here. I'll just write it off to the side using a separate color. That d dx of negative, or I guess just e to the negative x, is equal to negative e to the negative x. Just helpful to know, but if you don't memorize it, that's okay. You can always rederive it. It just shows up a lot. Cool. Let's do another one, another couple, and then we'll talk a little bit more about some special functions. So here we have this question. And, well, we just saw what the derivative of e to the negative x was, right? Like this e to the negative x kind of carried through. So maybe choosing, in this case, e to the negative x as u would work out because we can do maybe some cancellation. So let's do that. U equals e to the negative x. We just said that's the derivative is negative e to the negative x. So let's rewrite this. U times tangent of u times du over negative e to the negative x. But wait, we don't have anything to cancel that with. What we did was we took both of these and changed them to u's. But if we left this one as is, where we left this as e to the negative x, now we have something to cancel, right? And that's why we chose e to the negative x, because when we take the derivative, it stays basically the same. So we don't want to change this to u. So now we'll cancel this with this. This is negative integral tangent of u du. And now comes the hard part. Do you remember the integral of tangent? If the answer is no, that's okay. I kind of forgot it too, and you can rederive it on your own, but I'll give it to you for now because it's been a long video, and there's still some more to get through. So this would be negative, the integral of tangent of u is negative ln of the absolute value of cosine of u, and then add c. So this is just ln of the absolute value of cosine of u plus c, and we have to substitute this u back in. So ln of cosine of e to the negative x plus c. There we go. So for this problem, the main thing to remember is the integral of your trig functions, but also don't always change everything to u's because they can cancel out. Another one. So this one, kind of similar to the previous ones, but maybe not. Let's try doing u substitution again. Normally I say go with the denominator, but we can see pretty quickly why the denominator won't work out. The derivative 2x won't cancel with anything here. And if we choose e to this power, the derivative will be e to some power, and we won't have anything to cancel out with that. So now, basically the only choice left is this 3 to the x, and we'll just see what happens. So let's try that. 3 over x. U equals 3 over x, which I'll rewrite as 3x to the negative 1. Du equals negative 3x to the negative 2, just power rule, dx. Excellent. So let's rewrite the integral. We'll take care of the limits later. We have e to the u divided by x squared. Let's handle this separately. Dx equals du over negative 3x squared. So let's plug that in. Du over, negative 3x to the negative 2. So what does that look like? Well, when x to the negative 2 is on the denominator, we can just bring that up as a normal term. So this would be times du over negative 3 over x squared. So we can get rid of this and just multiply everything by x squared. And now we'll see a cancellation. So cancel this, bring the negative 1/3 out in front, integral e to the u du. We know how to do that. That's negative 1/3 e to the u, which is equal, well, but now we have to take care of the limits. I got a little bit ahead of myself. So let's solve for the limits. When x equals 1, u equals 3 times 1 to the negative 1, which is equal to 3. And when x equals 3, u equals 3 times 3 to the negative 1, which is equal to 1. So our bottom limit is 3, and our top limit is 1. So we'll be evaluating this from 1 down to 3. Let me just rewrite the limits here. And now we can use our fundamental theorem of calculus. 1/3 e to the 1 minus negative 1/3 e cubed. This gives us 1/3 e cubed minus 1/3 e. And that's our answer. So yeah, just a little bit more practice with that. Again, choosing nasty values for u is unfortunate, but sometimes necessary. And our last problem before we do a final bit of content and then a couple more problems, thanks for sticking with us. Let's do this one. Solve for dy dx. Seems like we're going to have to use some implicit differentiation. So let's do that. On the left hand side, we'll take d dx of 1 plus d dx of ln of xy. That equals d dx of e to the x minus y. So this first term here, that goes to 0 because that's just the derivative of a constant. And then we have the second term to deal with. So derivative of ln, we do 1 over that quantity and then multiply by the derivative of the quantity. So this would be 1 over xy times d dx of xy. And on the right, Well, the derivative of e to some power is e to that power times the derivative of that power. So this would be e to the x minus y times d dx of x minus y. So let's solve for the two derivatives separately. I won't rewrite the thing, we'll just solve for them separately. So d dx of xy, that'll use the product rule. So x times d dx of y plus y times d dx of x. So that's x times dy dx plus y. And then we have to find d dx of x minus y. So that's just equal to d dx of x minus d dx of y. So that's equal to 1 minus dy dx. So now we can substitute that back into our top equation. We get 1 over xy times x times dy dx plus y. And on the right hand side we have e to the x minus y times 1 minus dy dx. And we're trying to solve for dy dx, so let's try to do that here. Let's do a little bit of distribution and then isolate for the dy dx terms. So this becomes 1 over y times dy dx plus 1 over x equals e to the x minus y minus e to the x minus y times dy dx. Let's bring this term to the left and bring this term to the right. So we get 1 over y times dy dx plus e to the x minus y times dy dx equals e to the x minus y minus 1 over x. Factor out that dy dx. 1 over y plus e to the x minus y equals e to the x minus y over, minus 1 over x, and then we just divide by that term. E to the x minus y minus 1 over x, all of this divided by 1 over y plus e to the x minus y. That is our answer. A mighty, mighty beast of an answer, but we did have quite the strange equation. Again, this is just doing more practice with what we've learned thus far with e's and ln's. So hopefully now we're feeling a lot more comfortable. But perhaps you're still asking, hey, wait a second. We've only dealt with e and ln. What happens if it's like log base 2 of something? Or instead of e to the x, what if it's 2 to the x? Excellent question. Well, let's find out. So now we'll let a be a positive number, and u is still a differentiable function of x. Then, the derivative of a to the u is ln of a times a to the u du. So it's very similar to like e to the u, in that we still have that term there. Now we just multiply by ln of a. And I want to see if you can prove to yourself why this is true. And my hint for this is using the change of base formula. And actually do the same thing for this second one, where we're taking log of some constant of u that's equal to this. And the change of base formula will be really helpful here to prove why this is true. But again, we see the same thing where that 1 over u term is still present. Now we just multiply it by 1 over the natural log of that constant base. And then here we're taking the integral of a to the u, and this is similar to above, where it's 1 over ln of a, but then we keep this a to the u term. So let's do it in practice, and we'll do this first example. So this first example is similar to the first thing listed in our properties, where we have like a equals 2 and u equals 3x. So let's just write down the property here so we can reference it. A times a to the u du. So we can sort of just like plug into this here. So we'll get like ln of 2 times 2 to the u, which in this case is 3x, times du, well the derivative of 3x is simply just 3, so our answer is just 3 ln of 2 times 2 to the 3x. So that's the answer to our first question. So it kind of just a little bit of practice with the first property. How about this one? Well, if this was like 5 to the u, maybe we could handle that a little bit better. But since it's not, we can't yet. Unless we do some u substitution. So why don't we try doing that? We'll let u equal negative x squared, du equals negative 2x dx. And our integral becomes the integral of x times 5 to the u. Dx is now equal to du over negative 2x. We see that we have a cancellation here and here. This is negative 1/2 integral 5 to the u du. And with integral of 5 to the u, we'll use this equation right here. So this would be negative 1/2 times 1 over ln of 5 times 5 to the u. And we need to substitute our u back in, so this would be negative 1 over 2 ln 5 times 5 to the negative x squared. Don't forget your plus c. And that would be our answer. So that's using that third property there. Yeah, so how about this? Integral of 3 to the 2x over 1 plus 3 to the 2x. This is kind of similar to the example before where it was e to the x over 1 plus e to the x, I think. And the way we solved that was with u substitution. U substitution with the denominator, so we'll do the same thing. So du equals, well, what's the derivative of 1? That's 0. Derivative of 3 to the 2x, we can use the property that we just learned. So that would be ln of 3 times 3 to the 2x times the derivative of 2x, which is 2, dx. Let's just rewrite that. Dx equals du over 2 ln of 3 times 3 to the 2x. And see what happens when we plug it back in. So in the numerator we still have 3 to the 2x. In the denominator we have u. And here we have du over 2 ln of 3 times 3 to the 2x. Have a nice little cancellation. This term here is just a constant, so we can pull it out in front. And we're left with the integral 1 over u du. And that's going to be the natural log of the absolute value of u. And finally we do our substitution. 1 plus 3 to the 2x plus c. That's our answer. So a little bit more practice with u substitution in there, but now using a tougher value for u. One last thing that we need to talk about, which I call funky functions. So sometimes we run into functions that are really strange. So consider this, y equals sine x to the cosine x. The power is cosine x. The way we would deal with these is using a trick that we did at the beginning of this video, where we take the natural log of both sides to move this power out in front. So the natural log of both sides here would give us ln of y equals cosine times ln of sine of x, because that's using the properties of natural log. And this seems a little bit easier to differentiate, although we will have to use implicit differentiation. But that is the trick that we're going to use. So let's do a couple of examples. dy dx for y equals x to the x. So what we'll do is x to the x as a power is kind of weird to deal with, especially when x is the base. So let's try taking the natural log of both sides. On the right hand side, that x can come out in front, so we're left with ln of y equals x ln of x. And now we can implicitly differentiate. d dx of ln of y equals d dx of x ln of x. For the left-hand side, we've done this previously in the video, and we got this. For the right-hand side, we'll have to use product rule. So first times the derivative of the second, plus second times the derivative of the first. And just do some simplification. 1 over y dy dx equals x times, well, derivative of ln of x is 1 over x, plus ln of x times derivative of x is just 1. So this tells us 1 over y times dy dx equals 1 plus ln of x. So dy dx equals 1 plus ln of x times y, and we're given y up here, so let's do that substitution. 1 plus ln of x times x to the x. And that's our answer. Excellent. One more question. The slope of the tangent line of y equals ln of x to the cosine x at the point e, 1. So how are we going to do this? Well, we should take the first derivative to find the the formula to find the slope of the tangent line, and then evaluate it at x equals e. That's the game plan. So with this, it's being raised to the cosine x, so we should take the natural log. So we have ln of y equals ln of x to the cosine of x. So that means ln of y equals cosine of x times ln of x. Now we'll use some implicit differentiation. So d dx of ln of y equals d dx of cosine of x times ln of x. The left-hand side, we've seen it before, 1 over y times dy dx. The right-hand side will require the product rule. So cosine x times d dx of ln of x plus ln of x times d dx of cosine of x. So we'll bring this down, 1 over y times dy dx equals cosine of x, derivative of ln of x. So it's ln of some quantity. So we do 1 over that quantity, and then we take the derivative of that quantity, 1 over x. So that's what that would look like. We add to that ln of x. Derivative of cosine of x is negative sine of x. So we have 1 over y times dy dx equals cosine of x over x ln x minus sine of x times ln of x. We should multiply by y on both sides. So I'm going to get rid of this y, and we'll multiply this by y, but y is given here, so we'll just do the substitution all at once. Cosine of x. So we found dy dx, now we just have to evaluate it at x equals e. So we plug in e into this monster. So that would be cosine of e over e ln of e minus sine of e times ln of e times ln of e to the cosine of x. So we're going to make a lot of simplifications all at once here. Ln of e is just 1, so we're just going to erase this. This ln of e is 1, so we'll erase this, change it to a 1. Ln of 1 is equal to 0. So this goes to 0, which means sine e times 0 goes to 0. This ln of e goes to 1. And 1 to any power is going to be 1. So we're left with the cosine of e over e times 1, which is just equal to cosine e over e. And that's the slope of our tangent line. And with that, we've reached the end of today's video. It's been a really long video, but hopefully now you feel comfortable with the natural log and e to its different powers. There was a lot to go through, but hopefully you learned a lot and hopefully you did these problems with me. So that'll do it for today's video, and yeah, hope you have a good one. Until tomorrow. Take care.